Hey guys, today we're going to talk about a very critical concept, and that is that of bond energy. So when we talk about bond energy, what we're going to start by discussing is the theory behind what makes a bond. We're going to connect it back to Coulomb's law. We're going to talk about relative strengths of bonds, and then we're going to talk about the energies that it takes to break a bond and is released when we form bonds. So let's go ahead and get started. So let's start by defining bond energy. Bond energy is described based on the energy that it takes to break a bond or the energy that is released when a bond forms. Now, the more energy it takes to break a bond, the greater the bond energy, and the more energy is released when that bond forms, the greater the bond energy. So there's really two types of bonds that we're going to focus in on in this unit: covalent bonds and ionic bonds. So focusing heavily on covalent bonds, a covalent bond is going to be an interaction between a nuclei of one atom and the valence electrons of another atom. So what's going to happen is the nucleus of one atom is going to show an attraction for valence electrons of a secondary atom, and the nuclei of that second atom is going to be attracted to the valence electrons of the first. This is why we say that a covalent bond involves a sharing of electrons. What it really is it's a mutual attraction between two nuclei for the electrons of the other atom. Ionic bonds, on the other hand, are the bonds that exist within the crystal lattice structure of a solid ionic compound. Ionic bonds and covalent bonds are connected through Coulomb's law. And we're going to talk a little bit about Coulomb's law in a minute. But let's first start with the energy that is involved in bonding. Now, unlike in biology, where you heard perhaps that when ATP turns into ADP, energy is released, that is not what is really happening. I want to be clear about this. Bond energy, it takes energy to break bonds. It takes energy to break any attractive force, right? Think about it as two magnets. If I have two magnets connected to each other and I'm pulling them apart, it takes energy to do that. They are attracted to each other. To break apart the two nuclei that are attracted to each other's electrons, and I need to separate them in order to break a bond. Simultaneously, when a bond is formed, that is going to release energy. The process of forming a bond creates a level of stability that was not present before the bond is formed. So, remember this. It takes to breaks. It takes energy to break a force of attraction. It takes energy to break a bond. The energy that it takes to break a bond is called the bond energy or bond enthalpy. All right? Enthalpy, kind of like delta H, which we've already discussed. So we're connecting this back to thermochemistry. Let's show what this means in terms of that delta H now. So when we're talking bond enthalpy, what you have to remember is delta H of formation is the energy that is released when any compound is formed. Well, the heat of formation or enthalpy of formation is a sum of all of the bond energies within that compound. So we can use bond energies to predict the enthalpy of formation of a compound and then use that enthalpy of formation to then predict the overall enthalpy of a total reaction. So all of these are connected, but you have to be careful. Again, remember what's endothermic versus what's exothermic. Remember, the formation of anything in general is going to be considered an exothermic process because attractive forces are being formed. Formation of attractive forces, formation of bonds are going to be an exothermic process. It releases energy because you're making a more stable product in general. Conversely, when we're going to be breaking things apart, it's an endothermic process. So it takes energy to break bonds. So let's talk about what makes a bond stronger versus weaker. And again, I'm focused right now on covalent bonds. In a covalent bond, one of the factors that's going to make it stronger is how much electron density exists within that bond. Now, electron density is connoted by either a single bond, which has less density, than a double bond, which has less density than a triple bond. The more density of electrons within a bond, all right, the greater that bond energy will be because it takes more energy to separate the two atoms that are involved in that bond. So a triple bond by its nature is going to be a greater strength bond than a double bond, which will be a greater strength bond than a single bond. What does this mean? Well, remember, it's all about energy. It takes more energy to break apart a triple bond than it does a single bond. So when we look at bond structures, we'd expect a triple bond to have higher bond energy than a single bond. The second thing that's going to dramatically impact the bond energy is the length of the bond. Now, length of the bond is dictated in part by electron density, which we already talked about, but also in part by the size of the atoms involved in the bond. The larger an atom in the bond, the longer the bond length is going to be. Remember, the nuclei of these two atoms are going to be inherently repelling each other. The bond is formed by the attraction with the electrons, the valence electrons of the other atom. So the bigger the atoms are, okay, the more energy levels they have, the longer that bond's going to be, and thereby the weaker that bond will be as well. Okay, so a long bond is a weak bond. A short bond is a strong bond. Again, two factors that we're going to look at for relative bond strength. First, is it a single bond, a double bond, or a triple bond? And secondly, if I'm comparing between single bonds or between double bonds or between triple bonds, I'm going to then look at the bond length using the atom size as a proxy for the length of the bond. We can also look at the difference in electronegativities of the two atoms involved in a bond to help us predict the relative strength. Ionic bonds are extremely strong because each particle involved, each atom involved has actually become an ion. It's fully charged. And as we remember back to Coulomb's law, which is charge over distance, once you are introducing a full charge, now all of a sudden that force of attraction is increased. So the force of attraction in an ionic solid in the crystal lattice is going to be inherently greater due to its full charge component. Now, in covalent bonds, we're not going to see that full charge. Instead, we see things called partial charges. In a later unit, we're going to talk about partial charges, but here's the key. If a bond has two atoms that have differing electronegativities, electronegativity, remember, we talked about in Unit 0, and if they have different electronegativities, by that nature, the bond is going to be slightly stronger. The longer the difference, or the greater the difference between the electronegativities, the stronger the bond is going to be in general. But again, you're going to have to account for both the difference in electronegativities and the atom size, and also is the bond a single bond, double bond, or triple bond. Another way we can represent bond energy or bond length is actually on a graph. So what you see here is a graph that represents the relative energies of a bond at any internuclear distance. The internuclear distance is the distance between the two nuclei that are involved in the bond. Remember, low potential energy is stable. So the point at which we have the lowest potential energy, the bottom of that valley, represents the true bond length, or the expected bond length. The reason we have that is because of the fact that if the atoms get too close to each other, the nuclei are repelling each other. They're most positively charged. So as the nuclei repel each other, they're pushing each other apart, and it becomes less stable. The further apart we get, the attractive forces start to decrease. And so what we end up with is we get further and further apart, we end up evening out. That evening out is representing once the bond is broken. So again, two things that we can pull from this graph. The first thing we can pull from this graph is the bond length. Again, you're looking for the bottom of that trough, that bottom of that valley. That's the most stable point, and thereby that's the most likely length of this bond. The second thing we can pull from this is the relative bond strength. How much energy would it take to break the bond? That would be represented by the difference in the potential energy at the bottom of that valley all the way back to 0, where we've separated the nuclei enough to break that bond. So let's look at a concept as it pertains to enthalpy. Now, again, I've already mentioned this, and I'm going to repeat it. It takes energy to break bonds. And when bonds are formed, energy is released. Now, a bond energy that you're going to be provided represents the magnitude of energy that would either be absorbed into the reaction to break a bond or released from a reaction when that bond is formed. This is going back to our delta H. the energy of an exothermic process, the delta H of an exothermic process, is negative. The energy, the delta H of an endothermic process, is positive. But in this case, they're the same magnitude. Forming or breaking a bond is going to be the same magnitude. You just have to be aware of the sign. Are you forming, which would be a negative, or are you breaking, which would be a positive? So how does this connect mathematically to our delta H of a reaction? Well, first things first, you need to understand that the products are formed. And I already told you that forming products, forming bonds, is an exothermic process. So that means all the bond energies of my products would be made negative. So the delta H of my products is actually equal to the negative sum of all bond energies of my products. So I have to look at every compound within the products. I have to look at the bond energies within that, add them all together, and that's the delta H of my products. It's going to be negative because they're forming, all right? Attractive forces are forming, so a negative exothermic process. The delta H of my reactants is going to be positive, the sum of all bond energies. Why? Well, because any reactant we're breaking apart. We assume in any chemical reaction, and this is a good assumption, it's a safe assumption, every bond breaks and every bond forms. So the idea is when we look at the bond energy of our reactants, it's going to be the positive sum of all of the bond energies of my reactants, and that's going to give us our delta H of the reactants. So when we put this together, the delta H of a reaction is equal to the delta H of my products minus the delta H of my reactants. So if I look at this as a concept, as a skill, now I need to replace that with now what we've just found. So the delta H of my products is going to be negative the bond energy of my products. The delta H of my reactants is going to be positive bond energy of my reactants. So when I look at this and I actually do the math, what I find is that if I'm going to perform this function, then it looks like the delta H of my reaction is bond energy of my reactant minus bond energy of my products. However, the concept here is the same. You have to understand. Energy goes into breaking your reactants apart. Energy comes out of forming your products. If more energy comes out of forming your products, that means the delta H of your products is greater in magnitude than your reactants, the overall process is exothermic. If more energy goes into breaking your reactants than it does coming out forming your products, then the overall process is endothermic. So you can do this mathematically, but you can reinforce this conceptually. So let's go ahead and start with a couple of practice problems. Now again, these practice problems are going to represent the types of bond energy problems that you are going to see this year. So let's start with a fairly straightforward practice problem. I'm going to now use the bond energies given in the table below to determine the overall delta H of combustion of methane, CH4, with oxygen, O2, to produce carbon dioxide and water. So let's go ahead and get started. Again, we're going to go through and I'm going to show you each step of this process, so follow along. So now let's look at how we calculate this. We're going to start by looking at the sum of all bond energies of my reactants and then the sum of all bond energies of my products. So to find the bond energies of my reactants, what I'm going to do is I'm going to look to these Lewis structure diagrams. These diagrams show me how bonds are created in a molecule. In the future, you're going to have to draw these yourselves, but we haven't gotten to that part of the year yet. So in the meantime, I'm going to give you a diagram to represent the molecule. So as you can see, a methane molecule, CH4, is made up of 4 carbon-hydrogen covalent bonds. These bonds each have an energy of 413 kilojoules per mole. What this tells me is that my methane molecule is going to be comprised of 4 times the 413. Okay, so what I'm going to do is I'm going to take 4 times 413, and that's the overall bond energy of my methane molecule. That's not the only reactant, though. Oxygen, O2, has a bond energy of 495 kilojoules per mole. And the coefficient in front of that O2 is 2. That means I have to take that and multiply that value by 2. Be aware, this is an oxygen-oxygen double bond. And because we have 2 molecules of O2 present in this reaction, we have to multiply the bond energy of that O2 by 2, okay? That's going to then give me the bond energy of the oxygen. I've already found the bond energy of my methane. I'm going to add those together, and that's the total bond energy of my reactants. Okay. Now I'm going to do the same thing with my products. So I'm going to look at carbon dioxide, CO2. And again, I'm giving you the actual Lewis structure here. So what you can see is that CO2 is comprised of 2 carbon to oxygen double bonds. So 2 double bonds, each with an energy of 799 kilojoules per mole, which means I take that 799 and multiply it by 2. Okay, the coefficient in front of CO2 is just 1, so I don't have to worry about multiplying it due to the coefficient, just due to the number of bonds within the 1 molecule of carbon dioxide. I then look for the molecule water. Water is made up of 2 hydrogen to oxygen single bonds. So I look to my table here, I find the hydrogen to oxygen single bonds, and I see that the bond energy is 463 kilojoules per mole. Okay. Now there's 2 of those in every water molecule, and there's 2 water molecules. So I'm actually going to take that bond energy, I'm going to multiply it by 4 in this case. I then add that energy of my water to the energy of my carbon dioxide. So now I've found the total bond energies of my reactants and the total bond energies of the products. Now what do I do? Well, if you remember back to what we talked about just a little bit ago, the delta H of a reaction is equal to the bond energies of my reactants minus the bond energies of my products. Okay? So, why? Well, if we think about this as heat of formation, right, the reactants are breaking apart. It's a positive process. The products are forming. That's a negative process. So by saying bond energies of reactants minus bond energies of products, what we're really saying, if you do the algebra, is the heat of formation of products minus heat of formation of reactants, because you do the negative in front of the products, you do a positive in front of the reactants, you can flip them. All right, so it works mathematically speaking. But in the end, conceptually speaking, you think about what energy goes in versus what energy comes out. The energy in this case, if you add together the bond energies of all of my reactants, you get a value of 2,642 kilojoules per mole. So that's the total bond energy of all of my reactants. Then if you look at the bond energies of my products, you'll notice that you have a value of 3,450 kilojoules per mole. So what does this mean? This means that we put in 2,642 kilojoules per mole, and we got out 3,450 kilojoules per mole. If you think of this as like money, as currency, but in terms of energy, then we got out more than we put in. This is therefore an exothermic process, and the magnitude of my delta H in this case is going to be 808 kilojoules per mole, because that's the difference between the energy that was put in and the energy that we got out. So again, we can think of this algebraically or we can think of this conceptually. However you think of it, you need to keep the signs straight. You get more energy out than you put in. It's an exothermic process, and the delta H is negative. So again, the delta H of this reaction, this combustion reaction, it's going to be exothermic by its nature. That's part of the thing about combustion, is they're going to be exothermic, is negative 808 kilojoules per mole. So now that we've had a chance to practice on a slightly easier type problem, let's look at a slightly harder problem. Now this problem represents the combustion of ethane. And this problem, I'm again given the molecular structures, and I'm also going to be given the delta or the bond energies of each of my bonds that are going to be seen within my structures. My job is to figure out what is the delta H of the reaction and what is the endo or exothermic nature of this reaction. So let's go ahead and get started with this one. Now, as always in these problems, what I'm going to do is I'm going to start by summing or adding together all the bond energies of my reactants and then all the bond energies of my products. All right, so I'm going to keep them separate. Bond energies of the reactants. Now, ethane, C2H6, if you look at the structure, has 6 separate carbon to hydrogen bonds and has 1 carbon to carbon bond. So I have to account for all of those in the bond energies there. So I'm going to take the carbon to carbon bond energy, which is 348 kilojoules per mole, and I'm going to add it to 6 times the bond energy of my CH bond, which is 413 kilojoules per mole, and I'm going to add them together. That's going to represent the bond energy of my ethane, C2H6. Then I look at oxygen. Now, oxygen, O2, has a bond energy between the two oxygens. The double bond oxygen has a bond energy of 495 kilojoules per mole. Now, in this case, this is kind of weird. I'm going to multiply that by 7 halves. Okay, so 3.5. Why? Well, because that's the balanced reaction in this context. You know, if I wanted to multiply the whole thing by 2, I could, but in this format, this balanced reaction, it happens to be 7 halves. So I'm just going to multiply it by 7 halves. All right, so 7 halves times my 495. I add those two values together, the total energies of bonds within my ethane, the total energies of bonds within my O2, and I get the total bond energies of my reactants. I'm then going to repeat this process with my products. So if I look at my products, carbon dioxide and water, I'm going to take the CO2, looking at 2 C to O bonds within each. Each has an energy of 799 kilojoules per mole. And I'm going to multiply that 799 by 2, and then by the coefficient in front of the CO2, which is also 2. So essentially, I'm taking that 799 and multiplying it by 4. Then I look at my water. Each water molecule is comprised of 2 hydrogen to oxygen bonds. So I'm going to multiply the actual bond energy of my OH bond, covalent bond, by 2. All right, so the bond energy of my O to H covalent bond is 463 kilojoules per mole. Multiply that by 2, and then multiply that by the coefficient in front of my water, which is 3. So I'm essentially multiplying the bond energy of my O to H by 6 in this case. I then add the total bond energies from my carbon dioxide that I found to the total bond energies of the water that I just found, and that's the bond energy of my products. So when we look at the values, the total bond energy of my reactants added together is going to be 4,558.5 kilojoules per mole. And the total bond energy of my products is going to be 5,974 kilojoules per mole. So, when you think about this in terms of concept, we put in the energy to break our bonds of reactants. So we're putting in 4,558 kilojoules per mole. And we're getting out 5,974 kilojoules per mole, which means we're getting out 1,415.5 kilojoules per mole more than we're putting in. That would be an exothermic process, right? We're getting out more energy than we're putting in. So in the end, the delta H of this reaction is negative 1,415.5 kilojoules per mole. Okay? It is an exothermic process, as we would predict from a combustion reaction. So that wraps up today's video. Again, let me reiterate how important the concept of bond energy is within AP Chemistry. It is a critical subject and a critical idea that you need to be able to apply in a lot of different frameworks. We're going to really touch on this heavily in a unit when we start talking about molecular geometry and how molecules are actually made. I'd like to thank Caroline Woodard, Bonnie Liu, and Tiffany Lin for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one. Molecule, as you can see, I've got 2, oh my gosh, sorry. These practice problems are brutal. I'd like to, oh my God. Wow, did you stop? Oh. Not understanding completely the potential energy of the, no, I don't like that, hang on.